Hello and welcome to Lesson 3B. I can identify an altitude and a median of a triangle and use the properties of altitudes and medians to find missing measurements in a triangle. An altitude you've run into before. An altitude always connects a vertex of a triangle to the opposite side and is perpendicular to that opposite side. That's a long word, perpendicular. The altitude is also known as the height of the triangle. Now, the point of concurrency where your three altitudes intersect is called the orthocenter. So that's the new word for us today, orthocenter. Now, when I look at this triangle, it's really easy to see where my first altitude is going to go. Pretty clearly, we're going to draw it, let's do it in blue. We're going to draw it from the vertex. Not what I want. Come on, guys. From the vertex, straight down, like so, right? So that it hits at a 90-degree angle. Well, let's take a look at where we draw our altitudes for the other sides. Again, I'm going to start at a vertex. I'm going to move this way. But if I let it go right there, that's not a 90-degree angle. I'm going to keep moving until I hit something that appears to be 90 degrees. And that's where my altitude's going to go. And we're going to do the same thing here. I'm going to start at my vertex, come to the other side, I move it until I feel like I find something that's roughly a 90-degree angle, about there. Oop, I don't really like that. Undo. Well, close enough. So that you notice they're all going to intersect at the same point, right? So these are all 90 degrees, and they're all intersecting at this point. This point here is my orthocenter. We're going to do an activity in class later where we're going to actually find our orthocenters by folding paper so you can see them. There's the orthocenter. So an altitude is a segment that begins the vertex of a triangle and is perpendicular to the opposite side. So here you can see we've got this lovely triangle here, and we've drawn the three altitudes onto it, and they all intersect at one point, which is the orthocenter. So let's look at some properties of the altitude and the orthocenter. Three altitudes are concurrent at the orthocenter, and the orthocenter can lie in different spots depending on the type of triangle. The orthocenter lies inside an acute triangle, as we can see here, right there. The orthocenter is going to lie on a right triangle. Try that again. So if you look, there's an altitude right here. We've got an altitude here and an altitude here. They all connect, strangely enough, right at the vertex that always has the right angle. So that's going to be nice for us. And the orthocenter lies outside an obtuse triangle. So guys, your notes may not show this quite as clearly because your notes are printed in black and white, but if you look, this is the triangle right here. Okay, right here. And this time, my altitudes actually don't always hit inside the triangle. Remember when we were doing areas of obtuse triangles, and we noticed that the height of the obtuse triangle didn't necessarily fall inside the triangle. In that case, that's when we had to draw our altitude outside the triangle. And it just so happens that if we keep drawing it, they're eventually going to intersect outside the triangle. So just be aware that sometimes that orthocenter can hit outside the triangle if it's an obtuse triangle. Let's take a look at an example, and I'm actually going to change this example a little bit to make it a little bit easier on us. This should be the point 2, 0, since if you notice, my graph does not include any negatives. So find the coordinates of the orthocenter of triangle ABC with coordinate A at 0, 0. So here's A, B at 2, 0, there's B, and C at 0, 5. There's C. So let's connect them just so we can see. Beautiful. Now, if I want the orthocenter, that means I need to find the altitudes of each triangle. And remember, my altitude is perpendicular to the opposite side. Well, let's take a look at how we would do that. So I'm going to do the hard one first. This point 0, 0 right here. He's perpendicular to this line here, this line, which has a slope of, we go down 5 over 2, negative 5 over 2. So my orthocenter, or the altitude, sorry, of my altitude better have the opposite reciprocal slope, which would be 2/5. So when I'm drawing my slope here, I start at 0, 0, start at the vertex, and I'm going to go up 2 over 5. It's going to draw through that point there. I'm going to use a nice straight line this time to do that. So that is the altitude of that particular vertex. The other two vertices are much easier. If you look right here, this point right here is opposite this side over here. Well, anything if that side is perfectly horizontal. So to draw a line that's perpendicular to perfectly horizontal, we would draw a perfectly vertical altitude, which again I think I'll do in the black so that y'all can really see it. Perfectly horizontal, right? Perfectly vertical hits perfectly horizontal. And then similarly here, we'd start at 2, 0, needs to be perpendicular, it's going to go like that. So if you look, our point of concurrency is in fact at the point 0, 0, which makes sense. Because currency at 0, 0. This makes sense because it's a right triangle. In my right triangles, the point of concurrency is on the triangle at the right angle. So there we go. All right, let's take a look at our next kind of triangle. Our next kind of triangle, or the next kind of triangle segment, we're looking at medians. And a median connects a vertex of a triangle to the midpoint of the side opposite the vertex. The point of concurrency of my medians is called the centroid. And the centroid is the center of gravity or balance point of a triangle and is located 2/3 of the way from each vertex to the opposite side of the triangle. So let's see what that looks like. Let's say I start at this point right here. Well, I need to figure out what the midpoint of the opposite side is going to be. I'm going to look right here. I get out my ruler, which I think I may even have one of those in this clever little thing here. I get out my ruler. Come on, stop it. Sorry. The ruler, which is here. And nope. Okay, we give up on the ruler. We'd measure this side length and figure out that my midpoint is round about here, so that it would split that in two. Okay? Then I would simply connect those two vertices to get the median. Well, we do that for each side. I would go from this vertex over here. I would find the midpoint of the opposite side, which is round about here, and then we would connect so that that's even there. Then we do the same thing over here. For this vertex, I'd look at the opposite side. I'd find the midpoint so that we'd get this, and we would connect. And your midpoints are all going to meet at a point right here, and this point right here is the centroid. And the centroid lies along each line 2/3 of the way along the line. So if I were to start at the blue vertex over here and move along this line until I get over here, if I 2/3 of the way along this line, I'll hit the centroid, then I'll travel another third to the other side. So it really splits it up into an X and a 2X ratio, where the short piece is half the length of the longer piece for each side. So for example, for the red line, we could say it splits it into Y and 2Y, so on and so forth. So let's go to the next page. So now we've got a prettier diagram of a median. You can see there we created that on the computer. All of my medians are intersecting to find the centroid. The median is located 2/3 of the way along, and we've also detailed here in this diagram different ways you can break this up. That AG is equal to 2 times the shorter piece, or you can say that AG is 2/3 the length of the whole line, or even that GE is 2/3 the length of the whole segment. So there are lots of different ways to use these mathematically. So let's take a look at a couple of examples. Here they give me BG and GF. And when I look at this, I can see that I've got the longer segment, or the longer piece of my median, and the shorter piece of my median. Well, the longer piece of my median is equal to 2 times the shorter piece of my median. Okay? So when I plug in, that'd be 8x is equal to 2 times 32, or 8x equals 64, so x would just be 8. Now looking down here, they give me FB. Well, FB is the length of a whole median. Well, that again breaks into an x and a 2x ratio. So I know that x plus 2x must equal 18. So 3x equals 18, so x is 6. Well, that means that GF is equal to, oh, I shouldn't put a bar because it's a numeric value, right? GF is equal to 6. And BG is twice that length, which is 12. So that would be your answer there. So guys, that's the end of this lesson. I want you all to try the MML and come ask questions if you have any. Thank you.